Let's start today by a little summary of what we have discussed so far that's relevant to what we want to discuss today. And that is, first of all, that we saw that in conformal field theory the correlation functions are constrained, and we use the symmetry to fix the two-point function, fix the three-point function of scalar operators, specifically, meaning that the dependence on the points x1, x2, and x3 in the three-point function was determined, but still we had these undetermined numbers, the dimensions and the OPE coefficients. And so this was correlation function constraints. Then we went through this discussion of radial quantization and so on to motivate and discuss the operator product expansion, which is convergent. And then we discussed also unitarity bounds that have to be satisfied in CFTs that have a form like delta has to be larger than equal to some minimum value that depends on R, which is the representation under the Lorentz group that operators transform under. And then we said that you can use this, can be used in correlation functions to reduce them to correlation functions with lower points, with a smaller number of points. So this was sort of the summary, and this last part, that the OPE is a convergent, it can be convergent expansion, and can be used inside the correlation function, is the starting point for what we want to discuss today, which is crossing symmetry. And what is crossing symmetry? To discuss it, we'll do it by example, and the example will be very simple. We'll take the four-point function of one operator, phi. We'll assume that we have a CFT with an operator phi, a scalar operator phi, and we'll take the correlation function at points x1, x2, x3, x4, and we'll do the following. We will use the OPE, but we'll do it in two different ways. We will imagine a space-time configuration where we bring points x1 and x2 together, and then points x3 and x4, meaning that these 2 points are closer between them than these 2 points, meaning, let me just write it down, a configuration like where this is x1 and x2, and we can draw some sort of sphere around them, and x3 and x4 are sort of further away. I can enclose x1 and x2 in some sphere, I can enclose x3 and x4 in some sphere, use the OPE in this way, and obtain a certain decomposition, the conformal block decomposition of the four-point function that is going to look something like sum over all the operators. Sorry, there is a prefactor, 1 over x12 squared, x34 squared to the power delta phi, and then a sum over all the operators lambda phi phi o squared times that object we call the conformal block of function of u and v, as a function of u and v. Or I can exchange the positions of points 2 and 4, right? And I can consider kinematic configurations such that I bring 1 and 4 together, and then 2 and 3. This lower way of putting the OPE in will give us a separate conformal block decomposition. It will involve the same operators O exchanged in the phi OP, but now we are going to get a different prefactor because we're doing the OP in 1, 4 and 2, 3. There's going to be x1, 4, x2, 3 here, as opposed to x1, 2, x3, 4. And then G delta O L O. Now it's a function of V comma U as opposed to U comma V, because exchanging 2 with 4, you can see exchanges U and V, this conformal invariant cross ratios. And this function, the conformal block, is not symmetric in these two arguments, so this is a different function. Nevertheless, now the OPE is a convergent expansion. We imagine these two different configurations where you use the OPE in two different ways, but in the end it's a convergent expansion, so it must be that this is equal to this as an infinite sum, of course, in both cases. And equating these two results, these two conformal block decompositions, gives us the so-called crossing equation, which is of this form. Equals 0, where f, you can write it as follows. Okay, so this is, you see that when you equate them and you bring this over here, this is x1, 4, x2, 3 over x1, 2, x3, 4, and this is v over u. And that's why you get v to the delta phi here and u to the delta phi here. Okay, and then the rest is the blocks, and I have the infinite sum over here. Sometimes these f's are called convolved conformal blocks. Okay, so this is, after a little bit of algebra, the crossing equation, meaning a constraint of crossing symmetry on the 4-point function. Now one could also take another configuration where this point, this operator is joined with this, and then this one with this, so 1, 3, and then 2, 4. It turns out that that's certainly a constraint, but it turns out that in this simple case of identical operators, it is not something that is non-trivial. It relies, it can be satisfied block by block by a certain identity that this f functions satisfy. So it does not lead to anything interesting. Okay, so this is the crossing equation, and now we want to understand what we can do with this. And as we've done many times, the first thing to do when you try to understand something so complicated is to consider a limit. And now, it turns out that an interesting limit is, first of all, recall the change of coordinates from u to zz, uv to zz bar that we introduced last time, like this. Then we consider the limit z going to 0. Okay, and you might call this sort of, if you consider 2 to 2 scattering, you would call this sort of the S channel, and you would call this down here the U channel. Okay, so maybe I refer to them like this sometimes. I refer to these two sides of the crossing equation as the S channel and the U channel. So in the limit z going to 0, the left-hand side of the crossing equation, meaning the S channel, this over here, okay? Remember, the left-hand side, meaning I set them equal. This is the left-hand side and the right-hand side. And the left-hand side of the crossing equation, first of all, in the limit z going to 0, I forgot to write here that the blocks in this limit go like z to the delta, okay? Where delta is the dimension of that O that participates. And so in the left-hand side of the crossing equation, what I will get is the dominant contribution is going to be the one associated with the smallest possible delta. That's the dominant contribution. And the operator with the smallest possible delta in the CFT is the identity operator. It has delta equals 0. So in the left-hand side, the dominant contribution will give me 1 for the crossing equation, where I have assumed that lambda phi phi of the identity is 1, normalized it to 1, and this is, of course, in the limit z going to 0. So that's what I get from the left-hand side, the S channel. From the right-hand side, the U channel, I'm not going to prove it here, but it turns out, so remember, to go to the right-hand side, you exchange U with V, right? Because that's a function of V comma U there, meaning that you exchange Z with 1 minus Z and Z bar with 1 minus Z bar. So you make this change in the blocks and you re-expand them around Z equals 0. And you find out that each term, let me write it like this. So this is what you get from each term. You get a contribution from each term in the right-hand side that looks like this. It has a log in the limit z going to 0. So, of course, in the limit z going to 0, the log will give you a problem, will give you a divergence. So how can you possibly have the crossing equation work if on the left-hand side you get 1, and on the right-hand side you get a bunch of contributions, each one of them giving you a problem, giving you an infinity? Well, the only way for that to work is for another infinity to come in and save the day. The other infinity is the number of operators that you have to have in the CFT. There is no other way. The number of operators in the theory has to be infinite itself, so that this resums to something that reproduces this 1. Okay? So this is, again, in z going to 0. The conclusion from this is that crossing symmetry can only be satisfied. So crossing implies that we have infinite operators. To be more precise, infinite number of operators. In any CFT that, we use unitarity here implicitly by assuming that all these operators come with some coefficient here up front, but all those coefficients are squares, right? So they're positive. So we use unitarity. Otherwise, you could have cancellations, and I don't know what could happen, but any unitary CFT, you're just adding these things, and to reproduce the limit, you need an infinite number of them to get crossing to work. And this is a general feature of any conformal field theory that you might construct. So this is what you would call sort of an analytic treatment of the crossing equation. It allows you to use limits like this and discover general properties about the spectrum of conformal field theories, like, for example, that there has to be an infinite number of primary operators. Remember, these are primary operators. The sum over O that we're thinking about there is the sum over all the primaries in the theory, with the conformal block then summing up the contributions of all the descendants for every given primary that we are counting in the sum. So here, I don't mean an infinite number of descendants, I mean an infinite number of primaries. And each one of them has its own tower of descendants. Okay, so this is one important observation from the crossing equation, and another limit that can be used And by the way, you find, with a more careful analysis of this, you find that the operators you need have large dimension. So it's the large delta operators that you need to be infinite in number to reproduce this one. Of course, I didn't prove this, but a more careful analysis, you can show this. And then another limit that has been discovered is the one where you look at contributions of large spin operators. So there is such a limit where it doesn't matter what it is. It's not very important. It's this limit over here, where we recover information about operators with large spin. With large spin L. So in this limit, basically the logic is similar to what we did, but the conclusion is a little different. It says that at large L, in any CFT, there exist operators with dimensions delta, which take the form 2 delta phi plus 2n plus L plus 1 over L to some power that's bigger than 0, where this n and L are integers. L is the spin, and n is some integer, could be starting at 0 all the way to infinity. So you find, using similar logic to this analytic bootstrap logic, that there exist operators like this, and these are the operators you have in a free theory, because in a free theory there are operators of the type phi, then you have a lot of up to L free indices, and then you can take phi plus whatever is needed here to make this into a primary operator. This is not primary as it stands. You need to make it into a primary, whatever you need to add to do this, but nevertheless it's a free theory, so its dimension is exactly this. Without this part, in a free theory, it's exactly this. And so it shows that in any conformal field theory, no matter how strongly coupled, no matter how far away from the free theory you get, when you look at the spectrum at large spin, meaning the spectrum of operators exchanged in the phi OPE. So here we have in mind always the spectrum of operators exchanged in the phi OPE. When you look at a large spin for those operators, you find that the spectrum asymptotically looks like that of the free theory. Okay? So this is another result. I didn't prove this, but this is another result that you get when you look at the crossing equation in this analytic way, and by considering all these different limits. Okay. So what do you do with this now? Of course, one may look for more limits, try to analyze the crossing equation, and I mean, we'll transition to something a little different, which is the numerical bootstrap now. But before we go there, let me just say a couple of comments. That first of all is that we have focused on the 4-point function, but one could also use the higher point functions in the theory. So you take this phi operator, you can consider the 5-point function, the 6-point function, and so on. And you can basically use the same logic. Use the OPE, phi OPE, many times inside the correlation function, and try to reduce it down to a correlation function of lower points that you know. And this is an active area of research. People are, of course, trying to do this. And this is, contains information that you would consider if you were, that you would have access to if you were to consider correlation functions of operators in the theory beyond phi. So what I mean is that if you take, say, the 5-point function of phi, in the 4-point function, we took the OPE of phi with phi and then another phi with phi, and then the operators that appeared here were the same as the operators that appeared here. We got down to the 2-point function, we were done. Now, you take this OPE here and this OPE here, you'll get some operators here and the same ones here, but now you have another point, right? So you may consider the OPE now of this operator with the old operator phi. And this is an infinity of operators coming from this OPE. So, and then from what you get here, some O primes, you need to then further consider the OPE with this O, the 2-point function rather with this O. And of course, since you're going down to a 2-point function, this will be again the O's. But anyway, this logic tells you that the 5-point function, and the 5-point function will give you access to the OPE in this case of phi with O, OPE. While the 4-point function only gave us the information about phi with phi. So 4 points, we got only the phi OP. At 5 points, we got this as well. So you see, and if you consider higher number of points, things start to get, of course, a lot richer. So this is an active area of research. People are considering more points. And try to analyze the crossing equation using various limits. Because when you have more points, when you have 5 points in the 4-point function, more points means more crossing ratios, more conformal ratios. So instead of the U and V, the conformal cross ratios that you have with 5 points are more. So you'll be able to take more limits and analyze the results in different configurations to try to extract analytic results like we did for the 4-point function. Okay, so that is one comment, and one can find another comment here is that in general, all this, if you have 3 operators, O1, O2, or O3, what you can do is that if you take 4-point functions, all 4-point functions, and you use OPE associativity, where you do things like this. So, meaning that here you take the OPE of O1 with O2, and then the result is used to take the OPE with O3, versus if you take the OPE of O1 after you've done the OPE of O2 with O3, using the result of that OPE, then this we call OPE associativity, and demanding OPE associativity in all correlation functions at the level of 4 points is the same as considering 5-point functions, in the sense that 5-point functions will then be, crossing symmetry will be satisfied in all higher point functions if you impose OPE associativity in all the lower point functions, meaning even all the ones of all the operators in the phi OPE, it's an infinite number of them, all the operators in the theory. So sometimes, of course, this is not useful, this formal statement. It's more useful to consider higher points and get some encoded information about data in the theory beyond that appearing in the phi OPE. Of course, you know, that data is all together in some crossing equations, so it's not like easy to extract it. But nevertheless, sometimes it's more practical than considering more correlation functions. Okay. So why does this work? So let's try to see a little bit an intuition about why this bootstrap works, and that will be in a specific example. We have our crossing equation, and we have this f function that we have derived. And now, let's go to 4 dimensions, and now we know this function. We wrote it in terms of those K's last week. It was some 2f1 hypergeometric function. And I'm going to plot it, and I'm going to choose z equals z bar, okay? So, these plots are going to be at d equal 4, and I'm going to choose delta phi equal to 1, and I'm going to be plotting this f sometimes this is called the convolved conformal block, but you know. And we're going to plot it for, let's see, how do I plot it here? For value, so this will depend, of course, on delta and L, right? So let's look at it. Let's look at it. So this is a function of delta and L.
This what?
The thing I wrote as v to the delta phi g of u comma v minus u to the delta phi g of v comma u.
Yeah.
Yeah. So let's plot it for L equal 2. Okay, let's choose L equal 2 for this plot. And various deltas. And what you see, so this is 1. And this is 1/2. What you see is that it behaves like this. So let's say, I mean, you can go to Mathematica and plot this. This is not hard. And if you plot it for some higher delta, it does something like this. Let's say this is delta equals 6, and or here I have. It doesn't matter. So it does things like this. This is what it does. Okay? Okay. So this is a point z equal 1/2 where there is some, you know, local minimum. Okay, good. Now let's plot it for L equal 4, let's say. Again, the same axis, okay? But this is for L equal 4. And now it does sort of the same thing. So again, this is 1/2. And then this is as you increase delta. For example, delta equals 6, delta equals 7, and so on. So what do you observe from this? Well, that if I look at the point, I can look at any point here, z equals z bar, any point. But of course, it stands out to look at z equals z bar equal 1/2. If I look at that point, I see that all the second derivatives of this are positive, because it's a local minimum, right? At that point, all the second derivatives are positive. So let's write it the same way as before. And you know, you can make plots here for L equals 6, 8, and so on. You can go home and do this, and you'll find that it all behaves the same way. Okay? So, so this is true for L is 2, 4, 6, and so on. Very good. And I showed it for delta phi equal to 1, but you know, it's also true for some small epsilon distance away from delta phi equal to 1, where this epsilon is small. Okay? But of course, by unitarity, it's positive. We want the unitarity bound to be respected in d equal 4. Okay, so you see that I conveniently left out the zero spin plot. I started plotting from L equal 2. But now I can ask a question. Can it be that we have a CFT that has a scalar operator phi that does not exchange another scalar in its OPE? Can it be? So we have a CFT. Forget about phi squared. These are all perturbative type of arguments, right? That you have phi, you'll have phi squared, and so on. So these are all perturbative arguments. Can it be that there is a CFT where there is consistency with crossing and unitarity that we require, that exchanges in its phi OPE only operators of spin 2 and higher? Can it be? I mean, the answer to the question is obviously no. You don't have to know why. The phrasing is suggestive. So it cannot be, because I had this crossing equation. What was the crossing equation saying? The crossing equation was saying that these lambda squareds, f's, must be 0. No one stops me from taking the second derivative of this. Right? So I can just go and put this here. At that point and so on, right? And for those delta phi's and so on. Well, how can it be that this is 0 with positive coefficients if all these points are local minima of the f functions? It can't be. Okay? So there is no way you can find the CFT doing this. Now, this is in d equal 4, close to delta phi equal to 1, but I just wanted to give you an intuition as to how this works.
Why do you talk about second derivative? Because it seems that those plots you wrote there, it's all positive anyway.
I just have to find something to convince you that this is actually, something that how it works behind the scenes. I can go to any point in z and z bar.
If I just sum the values of the f's, I mean, if I sum positive numbers, I cannot also get 0. But it seems that even the value of f is always positive from your plots.
Yeah, but that's not generally so right, so how does it look if we plot the L equals 0 case? So if you plot the L equals 0 case, it looks like this. Again, we have the same labels. Now this is for L equals 0. And you get something like this. But then again, you start getting these things. So let's say this is delta equal 2, this is delta equal 3, but this is delta equal 6. Something like this. So not only did we prove using these arguments that we need operators of 0 spin, we also need at least one of them to not have too high a dimension, because then we start getting those positive second derivatives again. Okay? And therefore, crossing will tell us that there is an upper bound on the dimension of the leading scalar operator that we could have in this OPE. There's going to be at least one, let's call it the leading one, the one with the smallest dimension among all the ones you might have, but that one has to have dimension below a certain bound. Okay, so crossing here implies that delta of this operator must be smaller than or equal than to some delta critical. So, and this is the dimension of the leading scalar in the phi OPE. Okay? So even if you do have scalar operators with in the CFT, they can't have too high a dimension, all of them. There must be at least one of them at low enough dimension, below this critical value, which you can calculate. Of course, this is a very crude sort of way to try to calculate it. You can improve on this, but the point is that convexity properties of these f functions can be used to show these kinds of things.
But here you assume that there was a scalar at delta equal 1, right? Historically.
No, I assumed that there was a scalar phi. The only thing I assumed that there was a scalar phi.
But you wrote delta phi equal 1.
With dimension delta phi equal to 1. But in the phi OPE, this doesn't have to necessarily appear. right? Like in a regular weakly coupled CFT with a scalar phi, in the phi OP, you don't get phi. You get phi squared. But you don't get phi. Yeah, it didn't have to appear. It could appear, but it didn't have to. But if it doesn't, then this is, you're right. If it doesn't, then this argument, if it does, then the argument doesn't go through. But if it doesn't, then the argument shows that there must be another one with dimension below this critical value. Okay. So, I presented it this way using these derivatives, partly because I want to now, let's see, what time is it? Maybe we should take a break now and then present the logic and some of the recent results after the break. Okay. Crossing symmetry gives us upper bounds on operator dimensions here with these simple plots. So now we're going to sort of see how that extends and how the bootstrap is mostly used today to extract numerical bounds on both operator product expansion coefficients, these lambdas, as well as operator scaling dimensions, the deltas. And this is, again, a simple consequence of this crossing equation. And, you know, to see how these things arise, let's play some games. For example, let's assume here, remember, throughout we have assumed that there is a scalar operator phi. To make those plots, I assumed that delta phi was close to 1, but now I'm not going to make that assumption anymore. It can be anything, okay? But it's still a scalar operator phi, and the OP of phi with itself will exchange still the identity operator, say, okay? As a general feature. So now what we want to do is take this equation and choose some operator O0. Among the set of all the O's, let me choose one of them, O0. Okay? And then write the crossing equation as follows. I am going to separate the F associated with that operator out like this. I'm going to keep also the identity, and this has delta and L equal to 0, and I will normalize the OP coefficient of the identity to be equal to 1. So I'm not going to write, you know, there was a lambda phi 1 here, but I'm going to set that equal to 1 just by normalizing the operators. So I keep these two operators in this side, and I send everything else to the other side. So there's going to be an infinite sum on the other side of all the O's that are not the identity or this O0, right? Lambda phi O squared times F delta O LO. These are, of course, functions of U and V. I'm not going to write that. Or Z and Z bar in this picture. I'm not going to write the dependence on Z and Z bar. So this is a form of the crossing equation where I have isolated one operator, the identity on one side, and sent everything else to the other side with a minus sign. Okay? So what do I do with this? A similar thing to what we did. We start taking derivatives, but now we're going to take derivatives in a more complicated derivatives. We're going to consider a functional alpha, which I will write as a finite sum of over m and n, such that m plus n is bounded by some lambda I'm going to take this functional alpha. This takes a function of z and z bar, takes a bunch of derivatives on it, takes a linear combination of those derivatives with these coefficients alpha mn, and then sets z and z bar to 1/2. So that's something, takes a function, gives me a number, I can call it a functional, okay? Very good. And now I'm gonna, and it's a linear functional, so I'm gonna apply this linear functional onto that equation, okay? So what am I gonna get? Well, I'm gonna get that lambda phi phi O0 squared times alpha on this f of delta O0 L0 plus alpha on f0, 0 must be minus sum over the operators O that are not the identity or this O0 that we chose, lambda times alpha of that f of delta O LO. Okay? So this is the equation where I just acted with the functional, right? And now, what can I do with this? Well, I can assume some things. Assume the following. Assume that alpha of f delta O, comma LO, that those are positive. I'll just try to find a functional where this is true. So assume that I can find one where this is true, and also alpha on f0, 0 is 1, the number 1. So assume that I can do this, okay?
So this is a constraint on these coefficients alpha.
So among the space of such functionals, I'm trying to find coefficients such that that's true, yeah. And sorry, here I didn't mean to write 0, 0. I meant to write delta 0, delta O0, LO0. So this is the special operators alpha, okay? So alpha on the action of the block associated with the special operator, the one I kept on that side. While these are all the operators except, so this is except O0 and identity. This is true for all except O0, the special one. And identity, this is true for the special one. And I can always do this by rescaling. If I find one that is positive for this guy, I can just rescale coefficients to make it 1. So this is not very constraining. It's still the positivity condition. Okay, then what do I have? Then I plug them in and I find, so now this became 1 from that condition. And I can bring that to the other side. Minus an infinite sum of positive numbers times positive numbers. Right? So I have something is this minus something that's positive. So that means that it's less than or equal to that something. Right?
Aren't you missing an alpha f on the left hand side? Alpha f.
I set that equal to 1.
I set that, sorry.
Yeah, from my assumption of the choice of functional, yeah. So we proved, without appealing to any perturbative arguments or anything like that, that for any special operator you might choose, the OP coefficient squared cannot increase more than this minus alpha of f0, 0. So among the functionals that I have found that satisfy these conditions, I then search for the one that minimizes this. The one that minimizes minus alpha on the block, on the f associated with the identity, right? The one that minimizes this is the tightest bound I can get from this space of functionals on the OPE coefficient squared associated with this special operator O0. Okay? So you may call this a bound in some sort of interaction strength of conformal field theories. These OPE coefficients, you may think of them as interaction strengths in some way, where the phi OPE exchanges an operator O with some OPE coefficient lambda phi O. So you may think of them as sort of interaction strengths, and in this way we derive a bound on interaction strength in CFTs without any input from perturbation theory. So this is completely true no matter how strongly coupled the CFT can be. And it doesn't matter if it has supersymmetry, nothing matters. You'll always be able to get a bound like this. You just need a scalar operator to start with, whose 4-point function you are imposing crossing symmetry on. And of course, unitarity. Unitarity came in here because it allows us to say that after we put that assumption in here, this is this positive number, but the lambda squareds have to be positive independently of this. Right, the coefficients, and for that we require unitarity. So that's one way to use the crossing equation. The other way is to do something similar to this and write down the same crossing equation, and now what I'm going to do is I'm going to keep I'm going to keep only the block associated with the identity operator to this side and send everything to the other side. Well, I put the minus sign there already. So, so here this is just the O's other than the identity. So this is now a separate treatment, not like that. Times F. Okay, I can write the crossing equation like this.
Sorry.
Yes.
How can I make sure that my assumption here is always true?
I search for such a thing. And if I find it, then this is true. Is your question how there may be no, is your question that there may be no alpha for which this is true?
Yeah.
Yeah, I guess there could be no alpha for which this is true, but yeah, generically it is true. Generically we can find such alphas, but I'm not sure about proving its existence in general.
But to carry out this program, you need to know the full spectrum.
Yes.
So we'll get to that, to what I said, that there's no assumption from perturbation theory yet, but we'll get to sort of what assumptions are put in beyond what I've said. Let me finish this and then we'll get to that exactly. So, but you're right that there isn't, from what I've said so far, a general proof that such a thing exists. But you know, if it exists and we can find a few of them, then we can scan through them and find the one that minimizes this minus alpha on this f of the identity, and then we can carry out this program. Okay? Okay, very good. I can also use this equation. So and now, right, so here I have the identity on this side and everything else on that side. So what I'm going to do now is make assumptions about what these deltas and L's might be. I'm not going to make assumptions on these, but I'm going to choose 1 or 2 or 3 operators. I can choose however many I want, right, and make assumptions. For example, I can say that it has no scalar operators, like we said before, right? Or we can say that a scalar operator starts from dimension 20 or higher. Assumptions like that can affect 1 operator or 10 operators or an infinite number of operators, right? So make assumptions like that and then seek a functional, okay, alpha, such that alpha on the block of the identity is 1, and alpha on is positive. Let's say we can find such a functional. Okay, it doesn't have to exist, but let's look for one that satisfies these conditions. Then applying it on this equation will show that -1 is equal to a sum, if we assume unitarity, of positive times positive. Okay? Which is clearly nonsensical. So it must be that this assumption of unitarity that we made on the lambda squared is not true, that some of them are negative so that you can satisfy this. But within unitary theories, then we prove, if we can find such an alpha, that the assumptions we made are not consistent as unitary conformal theories. If we cannot find such an alpha, which is the other case, then we can't say anything. The assumptions we say are maybe okay, okay? You cannot say they are okay because you might find some other alpha, not in the space you looked for, right? Where this would be excluded. So no means no, but yes means maybe, okay? This is sort of the way this goes. No means I found a functional. If there was a unitary CFT, I would be proving that -1 is equal to a sum of positive things, which is nonsense, so there isn't one. Yes means I didn't find a functional, so I don't know. It could be okay. All right, so this is the logic in which we use the bootstrap. Now, this is always if we can find such a functional, okay? It might be, like here, you can see explicitly that we use the fact that we might or might not be able to find a functional to say something different, okay? It's the same also in that case. If we can find such a, typically in that case, we find functionals that exist, that satisfy these conditions. Here, we have this situation where we find or do not find such functionals. And to discuss now, what are the approximations involved? The other question we had. So here, the objection is that, well, you need the whole spectrum to do this because I need to verify these constraints for any delta and L, right? That I assume, and I already showed you that there's an infinite number of operators. So how can you possibly verify this? The answer is you cannot. So what you do is you truncate, okay? And it turns out that people initially, when they started applying this, they were discretizing in delta. So they were picking many points in delta for the operators they were considering. And then saying, okay, I'm going to consider, I don't know, 100 operators for every spin up to spin 20, let's say, here. Then people realized that actually you don't have to discretize in delta. You can make, you can phrase the problem in a way, I didn't show you how here, so that you can take this delta to be continuous from the unitarity bound and higher, but you still need to truncate in L, in the spin, okay? So you still cannot say, I'm going to check this for every L. I can impose this for any delta for a given L, but then I'm going to have to consider only finite L's that to check this on, because I'm doing it on a computer, say, scanning over this alpha and n coefficients. I'm not going to be able to check an infinite number of them. I'm only going to check a finite number of them for any delta, however. Okay? And you know, here what helps is the convergence properties of the OPE that tells you that you can truncate in L, and the error you're making is very, very small, because the OPE converges, and not only does it converges exponentially fast in the dimension of the, you can show in the dimension of the operator. So the higher dimension you include, the error you're making is e to the minus delta of the operators that you are neglecting. And moreover, the unitarity bounds tell you that if you consider high L, you necessarily include high deltas, right? Because the unitarity bound was, for example, for these types of operators was L plus 2. So there is nevertheless a truncation that you need to do in this spin, that you need to be careful. You need to take a high enough spin, and then numerically you get something. Then you increase the spin, and you see if it survives. And there is another truncation in the functional that you consider. So the functional that you consider has some alpha mn, and there was a bound, a sum, sorry, where this m plus n was less than or equal to some lambda parameter. So that is also sort of a limitation. But you can also increase that lambda parameter and find functionals that are sort of stronger in some sense. However, if you are able to exclude something with a certain choice of lambda, that will remain excluded if you consider a stronger functional, right? Because you can always take 0 for the coefficients of the stronger functional and reduce back to the old functional, which you used to exclude already something. So something that was excluded, something for which, you know, we managed to show something like this, will stay excluded no matter how stronger numerics we use. However, something that's allowed, we may consider a stronger functional and then disallow it. So that's why a yes is a maybe. It's not a definite yes. Okay? So these are sort of the approximations involved.
But the idea is that you want to find so universal results that would apply to any CFT, right? Because here you assume that this alpha bigger than 0 is valid for any values of delta. But if you look at a specific model, you have some discrete points, and you may find like better functional.
Exactly, yes.
Yeah.
Yes. We want to find, imposing this in general forces us to not make any assumptions from the beginning. But if we do want to go to a certain theory, then we can do things like that as well. But if you're interested in general statements, you can't assume that from the beginning. Okay. So this is sort of the logic, and what does this logic give? Let's see what it usually gives. And I'm going to focus more on the logic on the left board there. Which allows us to get bounds on operator dimensions. And just to clarify, it could be that you don't get a bound from that. But it could be that you don't get a bound from this construction over here. So on the OPE coefficients, in some cases, it could be that you don't get a bound. In that case, you only have a lower bound from unitarity that lambda squared is positive. Okay? So that would be then the only bound you get in that case. So let's talk about now. So this was, again, just phi, what I'm going to plot now. People applied this logic and they said, okay, let me make the following assumption. I'm going to have this operator of dimension phi in the theory. I'm going to look at the 4-point function of phi with itself. And then I'm going to say, in that 4-point function, there is some operator. We know that there must be some scalar. So there is the identity. And then the next operator is something we're going to call phi squared. But this is just a name. Okay, phi squared here doesn't mean the perturbative phi squared, right? It means the leading operator that appears in the phi OP, whatever that is. Okay, it's just a name. So, okay, of course this plus ... includes other scalars and includes higher spin operators, okay? And then we're going to say, let me plot, try to use that sort of argument to see what I can get for the dimension of phi squared. So I'm going to go here, and these assumptions are going to say L0 is 0, because LO is 0 because I'm looking at phi squared, and delta phi squared, I'm going to now vary what I choose for it. Okay? And if I choose something reasonably small, down here, it seems okay. So I choose my delta phi, I choose my delta phi squared in there, and I leave everything else to start from the unitarity bound, okay? But I say that the leading scalar is from some value and above. I don't allow it to be below a certain value, the leading one. Then there could be an infinity of subleading ones, but the leading one will be at some value and above. And then it's okay, if I choose this value low enough, it will be fine here. But if I suddenly choose it very large, it's not going to be fine anymore. If I choose it very large, I am able to find a functional that makes this happen. And then I know I violated unitarity. So unitarity and crossing will tell you that there is some curve that separates the two regions. And the curve looks like this. Okay? Where the check marks mean that the unitary CFT can exist with that choice, and the X means that cannot exist with that choice. Okay, so this is sort of what you get, and this is what people, so this was first applied, this whole logic was first applied, discovered and applied in 2008 in a paper where in D, so this was D equal 4. This was a plot people obtained, and you know, this here, the starting point for this plot was 1 and 2 in D equal 4. Delta phi is 1, and delta phi squared is 2 if you had a free theory, right? So the plot allowed the free theory, of course. And then it showed that adding interactions, meaning giving an anomalous dimension to delta phi, has some sort of correlation to what anomalous dimension delta phi squared can get as a maximum value, no matter how strong the coupling. And this gave rise to this curve, okay? So this was one of the first results. And then another application of this method was in D equal 3. And in D equal 3, there is a lot of motivation for understanding conformal field theories because of what we showed even in the first lecture, where we talked about the Ising model and the critical point of water and all that stuff. Because this fall under the category of classical critical phenomena, where you have this, remember, you have this competition between temperature, right, and the various parameters in the Hamiltonian that try to align the spins. Temperature tries to randomize them, and you get this competition and this critical behavior. So this is called, you know, classical critical phenomena. And in D equal 3, there is tons of them. Okay, and they're all described presumably by conformal field theories. So this method was then applied in D equal 3 to understand some classical critical phenomena. The first one is, of course, the Ising case. And in the Ising case, you have a scalar operator. In the literature, it's called typically sigma, not phi. But it's just like that phi. Sigma because it comes from the spin in the Ising model, you know, for that spin that was either pointing up or down, S we called it. Well, now you call it sigma because you also know the Greek alphabet. So, and then you say in the sigma sigma OPE, it's going to follow exactly like that rule. There's going to be the identity, and then the leading scalar. The leading scalar after the identity, people call it epsilon. But it's like that phi squared. But it's a strongly coupled theory, so now we have to give, you know, that's also a strongly coupled theory generally. So phi squared was just a name, that's why I put it in quotes. Now that name became epsilon, okay? And this is like sigma squared in the sense that it's like the energy associated with the configuration of spins, like sigma squared, okay? So, okay, so can I get a bound on delta epsilon as a function of delta sigma? The only thing that changed now is we went from D equal 4 to D equal 3. Nothing else changed. But the blocks are now different, because the blocks used to have to satisfy some conformal Casimir equation, and D appears specifically in that Casimir equation, so the solutions will be different. Okay? So now we do this with the blocks of the D equal 3 theory. Okay, so and what we find, and that was sort of a surprise at the time, we find something like this. You find a bound that starts at the point 0.51. So a scalar in 3D has dimension, you know, d minus 2 over 2, so that's 1/2 in d equal 3. So it starts at 0.51, which is the free theory limit. Then it starts to go up. And remember, everything here is allowed, everything here is not allowed. And then it has a kink at this point. So it goes up, and then it turns and tries to go to the right more. And this was a surprise. And when you look at the numbers where this kink occurs, is 0.518 and 1.41 for the y coordinate. And those numbers turn out to be exactly like the numbers that people have determined with epsilon expansion methods or other methods, or experiments have in fact measured for the Ising case. Okay? So this, of course, was quite a surprise and created a lot of excitement that these bounds do not only give you some generic curves like they did in d = 4, generic curves seem to also pass very close to points where you know actual CFTs might live. And here, the actual CFT is the Ising CFT. So people said, well, you know, the bound, if it was, why did it develop this kink? Well, if it wants to go from here to here, right? But there is sort of a CFT in the middle, so it has to go up first and then go to the right, kind of. So this is the idea why this kink appears. The fact that you have this physical theory there has to be accommodated by the bound, and this creates this kink. Now, it's not necessarily true that anytime you have a physical theory, you will get a situation like this. But here, it happened. And, of course, then people started analyzing this more. So the next thing they did is try to get access to more of the spectrum of the theory, because now we want to consider sigma OPE, and sigma has a Z2 symmetry, as we were discussing for the Ising case. So this epsilon is a Z2 even operator. Sigma is Z2 odd, epsilon is Z2 even, and this is the bound. But now, instead of just considering sigma and getting access only to the Z2 even part of the spectrum in the sigma OPE, you might as well consider sigma epsilon, and then you can do the OP like this, or you can do it like this. And if you do this, maybe you still only get access. Sorry, you now get access to the Z2 odd part of the spectrum. But there is another way to consider this 4-point function, another ordering, like this, where now I can do this, and now I get a crossing equation involving both the Z2 odd part of the spectrum from this side of the crossing equation and the Z2 even part of the spectrum on the other side of the crossing equation. In other words, when I told you in the previous hour that taking the T channel was trivial, right? Here, when you have different operators, it's not trivial anymore. Okay? So you could take sigma epsilon and sigma epsilon, and that would be an independent equation. So here I can do the same by changing the ordering and using the U channel again. Okay, I didn't do anything. And then it turns out that you can also add this correlator, which is necessary in order to be able to set up the numerical problem the way we have described. You also include this operator, and you analyze the whole system using exactly the same logic as we did before. And if you look at that system, you are going to see that things get a little more complicated, but in the end, the logic will work exactly the same. So what do I mean by this? So let me write some equation there. For how things look when you have different scalar operators. These are all still scalar operators. Now the prefactors are a little different. So if you have the 4-point function phi1 at x1 up to phi4 at x4, and you write this thing down, then things get a little bit more complicated. And then you have a sum So it's a little more complicated. The prefactor is more complicated in that it involves this numerator, which depends on the differences delta 1 minus delta 2, where delta 1, delta 2, delta 3, delta 4 are the dimensions of phi 1, phi 2, phi 3, phi 4, which appear there. And then the blocks also depend on this difference, delta 1 minus delta 2. It's not just these delta O's that are labels, these differences are also labels. And then you don't get a square here, obviously. Okay? So now you cannot easily say, well, yeah, let me assume that this is positive. It's not the square of anything. So they can both be real and the product can be negative. So unitarity will not imply that the product is positive. So, you know, the other two things are fine, whatever, it's just more complicated to deal with this and that. You can just do it. This is something you have to deal with if you want to apply these positivity requirements the way we were presenting them before. And it turns out that you can deal with it, but by making the problem into sort of a matrix problem. So now instead of requiring positive things, you require positive definiteness of some matrices that appear. And again, you can apply the same logic as we had before. So let me I don't think it's very helpful to go through these steps. I can give you guys a reference, or you can try yourselves to write down these 4-point functions using that equation over there and get the corresponding crossing equations from doing the OPE in all these different ways. So here you can do it this way. Here you can only do it this way. This way. Here, the 4-point function involving sigma and epsilon, you can do two different things. So here you're going to get, in fact, 5 independent crossing equations. It looks like 4, but you're going to get 5. And you will then be able to arrange things in some matrix form, which will look like this. So I didn't show you the steps for all this, but there will be, in the end, a certain form like this. Let me write it like this. Right, this is 0 where this is a 5 vector and this is a 5 vector of 2 by 2 matrices. What is in this 5 vector? This F. But now there's not only one F, there's an F plus and an F minus when you decompose things, just because of that complicated prefactor and so on. So these matrices contain Fs, and this is some vector, 2 vector here. So this matrix contains 5 2 by 2 matrices containing those Fs. But this is just a 5 vector of those Fs. Okay, and they have some zeros, it doesn't really matter. The structure is what matters. Okay. And now what can I do with this to show that it works the same way as before? Well, I'm going to have a functional now alpha, which is itself a vector.
This is from the set.
From all these crossing equations, you can put them in this form. And now I'm going to consider an alpha, which is a vector, alpha 1 through alpha 5. And I'm going to take this vector and take the dot product with that crossing equation. So from these 5 different equations, written in vector form here, I'm going to get one equation. Because I take the dot product of this vector with that equation, I'm going to get one equation, which will, however, involve 5 different functionals, like we had before. So now I have more freedom. I'm going to be choosing coefficients for all these 5 functionals completely independently. It's a bigger problem, right? But I'm going to be making those choices, and I see that I have in the sigma sigma OPE, I have this O plus operators, where by O plus here I mean the Z2 even operators. The plus means Z2 even, where the Z2 symmetry is the symmetry is generated by sigma going to minus sigma. So that's how you generate the Z2 symmetry. And by O minus here, I mean the Z2 odd operators, the ones that transform in the sign representation, okay? We have the Z2 even, the Z2 odd operators, and we can find this crossing equation. So now we have access to the Z2 even part of the spectrum as well as the Z2 odd part of the spectrum. And we can make plots for the dimension, say, of the first operator in the sigma epsilon OPE. So what do you call the first operator in the sigma epsilon OPE? You call it sigma prime. And that's a general notation in these models. So the first operator in some sector, you call it, say, sigma. Then the second one will be sigma prime, then sigma double prime, and so on. That's sort of the notation. So in the sigma sigma OPE, we had this epsilon. The next scalar, that is Z2 even, will be called epsilon prime, and so on. Okay? If you look, then as a function of sigma, what is the dimension of sigma prime? Okay?
So sigma prime is the one that appears in the sigma epsilon.
Yeah, let me write it here. Yeah, that's right, yes. So sigma times epsilon now does not have the identity. The identity is in the sigma sigma OP, is in some sense Z2 even, right? But it will have sigma as the first operator back, and then sigma prime, and then more operators. Okay? But I'm looking at the dimension of sigma prime as a function of the dimension of sigma, and the plot looks like this. Where this is 3, and this is again that 0.518. And everything down here is not allowed, is allowed, but out here is not allowed. So now we got this spike up here, and now we know what to do. If we know what to do to isolate a theory. We can say, if I make the assumption that the sigma prime has dimension bigger than 3, then I will only be allowed to have delta phi's in this region over here, right? I'm cutting off the rest. This is the only thing allowed. And so using this mixed correlator system, what you end up finding, if you plot it back, the delta sigma, delta epsilon plane, assuming that sigma prime, and you also assume that epsilon, sigma and epsilon are the only relevant scalars, then you get some solution here, which is disconnected from some bulk of solutions here. So what you do is you get some allowed region here, and then some allowed region here, and everything in between is not allowed. You have to make these assumptions. and use the full system. And this region is again the same. Okay? So you were able to go from a kink to an island in theory space, where you have this idea now that, oh, this must be an island because it's an isolated theory that lives there, that is not closely connected to any other theory around it. There's still sort of a continuous allowed region farther away, but this theory is special. At these points, with these assumptions, there can only be one theory, and that's the Ising theory. And that's why we got this island to pinch off the rest of the allowed region.
Wait, it's an island because you've decided to...
I decided to make...
it off from the rest.
I decided to say that, well, all I decided to say is that sigma and epsilon are the only relevant scalar operators, one z2 even, one z2 odd. And in the phase diagram of water, you can say that this is an assumption about the critical point of water, because there I have to tune two parameters to go to the critical point. I have to tune the pressure and the temperature, right? The pressure corresponds to sigma, the temperature to epsilon in some sense, right? So two relevant parameters, I tune and I go to the critical point. Here, I tune two relevant parameters again. I don't tune them, sorry. I am saying that there are only two relevant parameters, the ones associated with sigma and epsilon, or all the other ones are irrelevant. Sigma prime in particular is irrelevant. And epsilon is also irrelevant. Epsilon prime, rather, is also irrelevant. And then it pinched off itself. That's the only assumption I made.
But you also decided that sigma prime should have dimension bigger than 3.
Yeah, which means that sigma is the only relevant operator. It's the same assumption.
Yes, but what I'm saying is that already on that plot, you're already creating an island by...
Yeah, here I was motivating how you can get an island, basically. Yes. But you see that, you know, I didn't have to show you this plot, so forget it. If I make those assumptions, I'll get the island. Then you can understand that you get it by a combination, by sort of an argument like this. You sort of trace back how you got it numerically. And so this is this method. Again, this is obtained from this whole system using this 5-vector of functionals. And people then, of course, once they got the island as well, they got very excited, and they started determining, using functionals that are stronger to shrink the island. And they shrunk it so much that they got to a precision that is a factor, an order of magnitude better than, you know, whatever method existed before that was the most accurate at the time, which was a Monte Carlo method for the determination of this delta sigma and delta epsilon. So, okay, that was very, very impressive, and it completely validated the method, right? I mean, you had a method, you reproduced something that you knew existed, the Ising case, and not only did you reproduce it, you enhanced the precision at which you knew the critical exponents of that theory. So this is, you know, this method now can be applied in all sorts of different settings. You can apply it if you have a theory with a global symmetry that isn't just some Z2, can be any global symmetry. You can apply it in the ON model. You can apply it in any dimension. You can apply it for theories with supersymmetry or not. And you can look for bounds like this, try to find islands, try to motivate the existence of CFTs, and every result you're deriving is non-perturbative and does not, well, of course it has the assumption associated with truncating that we discussed, but this truncation due to the convergence of the OPE is sort of under control, and you don't have to worry too much about it. Of course, you always have to test to make sure that your results are not truncation dependent. So in other words, you have to include a high enough number of spins to get trustworthy results. But you do all this, and you can derive completely general and non-perturbative results in a variety of conformal field theories across dimensions and with any symmetry that you want. So this is the method. Of course, these days, there, initially people were writing their own code to try to do this on the computer, and then eventually some tools appeared that you can now use to start running bounds like this and finding constraints on conformal field theories. So it's largely now you can treat it like a black box in a sense, where you only have to specify the problem, and then all the algorithms required for you to run to run this logic numerically are ready to be used. Getting the blocks, getting all the approximations going that you need, and so on. All that has been implemented, and you can use it. Any questions? Yes.
So coming back to this comment, you said that so when we draw these lines, it appears that no theories live on these lines. Like the Ising model at the kink.
Yeah, it happens to lie there. Yeah.
So I would say either it's a coincidence or there's a principle that discards the lower, the region below that line as well. Because there's no reason. If you say it's allowed, then you could have no theories in the middle.
Yeah, I think one way to say it is that, it just so happens, it didn't have to be that way, but it just so happens that among the space of consistent CFTs, the Ising model at that dimension for the sigma operator maximizes the anomalous dimension of the epsilon operator.
So in that case, you would call it a coincidence, but maybe could it be that there is an argument to actually discard everything below that line as well? And then you're forced to have all your theories. Yeah,
in order to discard things below the line, you can start playing with things like this, making assumptions. Remember, this we did not get generally. We got after we imposed assumptions. So if I say sigma prime was above 3, like there, but epsilon, I allowed it to be below. Epsilon prime, I allowed it to be below 3. So that epsilon is not the only one. So then, what I would start getting is, it would start to look like this. You would get plots that had a connected region like this. And then this gets narrower as you increase, and then of course this is included. It gets narrower as you increase epsilon prime dimension, the epsilon prime dimension. And once you cross 3, you see that it pinches off, and then you get the separation. So playing with assumptions allows you to sort of carve out the region in parameter space that's allowed. But in the end, it's all because of the assumptions you made that you were able to make this separation between an island and another allowed region. So you see, we didn't solve the theory, we didn't do anything. Essentially, we just used crossing equation. We didn't solve the theory. We didn't find the solution of the Ising model with some very clever method or anything. We just said that with these assumptions in the spectrum, there is there is a very specific way to satisfy them that is consistent with the spectrum of this Ising theory. There are other ways to satisfy them out here, but we know the Ising theory lives here, and that's isolated from the rest. So, of course, people said, oh, this is a solution of the Ising model and so on. Of course, it's not a solution of the Ising model that we want. It gives us very good data for the Ising model, but it's not a solution in the sense that the 2D Ising model has been solved. Obviously, right? But if you have a good data from a perturbative method, say like the epsilon expansion, now you have a non-perturbative method to compare with. And you can do this for the epsilon expansion in many cases, and for example, the epsilon expansion works very well with the non-perturbative data. So it's a very valuable method because it doesn't rely on perturbation theory, but it's a numerical method. And we have, of course, strong coupling here, so perhaps that's the best you can hope for. But certainly it's not like a method an analytic method that you can solve. What we like as physicists to have an analytic method to solve something, right? But it's good enough for some things. Of course, it has another disadvantage is that it provides you a spectrum. It says, if you didn't know anything about the Ising model, nothing, right? You would say, well, okay, if I impose Z2 symmetry and make these assumptions, then I get some island here and some other region there. Doesn't tell you anything about a microscopic origin for the CFT that may live on that island. It just gives you a spectrum. Says, here you go, there is a consistent spectrum of a CFT. You have no idea that this is in the same universality class as some spins that you put on a lattice, and you take some continuum limit, and you have no idea about any of this. You just get a spectrum, which, you know, is a limitation of the method. Nevertheless, it's a very powerful method as far as deriving results for non-perturbative results for the spectrum of CFTs. You can use it to derive general results, as we showed, and also specific results for theories that you care about. So in that sense, it has really revolutionized our understanding of conformal field theory and the spectrum, the general properties of the spectrum of conformal field theories, as well as the spectrum of specific theories. All right, that's all I had to say, and unless there are more questions. All right, very good.